The purpose of this experiment was to explore the behavior of the magnetic field produced by a real and simulated magnet. To do so, I used derivations of the Biot-Savart law to make predictions about the magnet's magnetic field. Some derivations that were helpful for this lab include the magnetic field at a location on the axis of a magnetic dipole. The mu present in this formula is equal to a current multiplied by an area. Another derivation is the magnetic field at a location perpendicular to the magnet, which is half of the on-axis field at the same distance. For the first part of the lab, I used a magnetic sensor on my phone to measure magnetic fields produced by a bar magnet. For the second part of the lab, I coded a simulated model of the real magnet. For the experimental part of the lab, I used the magnetometer map on my phone to measure magnetic fields at different distances away from the magnet. To do so, I attached a magnet to the end of a matterstick and measured the strength of the magnetic field produced at a few distances away on axis to the magnet's dipole. Next, I found the average distance of where the net magnetic field was 100 microteslas. Using this distance, I moved the magnet back and to the left by that value and recorded the x, y, and z components of the magnetic field at this off-axis location. With all the data captured on a spreadsheet, I could plot the on-axis data onto a graph with the horizontal axis as the natural log of the distance and the vertical axis as the natural log of the magnetic field. By using the data's line of best fit and the graph's relation to the Biot-Savart law, I could identify the constant being multiplied to 1 over distance cubed. Through manipulation of the y-intercept from the graph, I calculated the dipole moment of the magnet. First, I took the value and raised e to the power of that value. Then, I divided the result by mu naught over 4 pi. Then, I divided that number by 2. The resulting value I found for my magnetic dipole was 3.08 amperes square meters. For the code part of the lab, I used Python to simulate a magnet with the same properties as the physical one I used previously. First, I established some constants using the mu of my physical magnet and created a magnet object. Next, I coded a function that would calculate the strength of a magnetic field given any dipole moment and distance vector. Then, I set a scale for the magnetic field, a distance away from the magnet, to observe the field at, and created 6 arrows that would display the magnitude and direction of the magnetic field at their separate locations, parallel and perpendicular to the magnet's dipole moment. Finally, I created another arrow that would observe the magnitude and direction of the magnetic field at a location off-axis of the magnet's dipole. When comparing the numbers from the measured magnetic fields to those of the simulated fields, I found that they are not equal, but they are not too far off from each other. One key difference between the two cases is that none of the arrows in the simulated model have a z component to their fields. Some possible errors in the experiment include technical errors with the magnetometer chip in my phone, as it may have been inaccurate at times. There could have also been an error in accurately recording the correct distances. What if I hadn't oriented my experiment to compensate for the magnetic north? If my phone was angled in a different direction throughout the experiment, the x and y components would both change according to the new direction of my phone and the direction that points north. What if I stuck 2 identical magnets together end to end and reran the experiment? If I were to do this, the magnetic field produced by the combined magnet would be about twice the strength of the single magnet. The distances from both parts of the experiment would decrease due to this change.